Classifying functions. So we're mostly focusing on quadratic functions, but I'm bringing back constant and linear functions a little bit just to kind of make some comparisons for you. I'm really going to want you to try to focus more on those quadratics. It's really where we're going to be kind of headed. So just to review with you a little bit about the parent functions, we have our constant function, our linear function, and our quadratic function, okay? So the constant functions are functions where the equation is usually those two that we talked about, our vertical and our horizontal lines where the slope is not positive or negative. This is a zero slope, and so those were our horizontal lines, and they oftentimes looked like f of x equals b. And then these were our vertical lines where oftentimes they looked like x equals b. This one could also be written as y equals b. So we had our horizontal and our vertical lines. When we talked about slope, we talked about the difference between those two. Those two are considered constant functions, okay? Their degree is 0 because there's no term in it that typically has a function. This is an x to the first. This is an x quadratics or x squared. This is usually an x to the 0. So if it's x to the 0, that means it's equal to 1. In other words, there's no x term. It's just some number. We're just going to plot that line in there. It's not really an equation, so to speak. So it has a degree of 0. This one has a degree of 1. This one has a degree of 2. We just said that. The shape of these two, this one is either horizontal or vertical. There's just no choice other than horizontal or vertical for those two lines, okay? Those are your constants. Your linear functions are ones that actually have a calculated slope, so it's rising or it's falling. Its shape is a line, and usually it's written in mx plus b form or slope-intercept form. So the function says f of x equals mx plus b. Remember, that's the functional form of a linear equation that looks like y equals mx plus b. So this is the linear equation, and this is the function, okay? The last example has a shape. We call this shape a specific name. We call it a parabola, not a parabola, a parabola, okay? So it makes this shape where it turns. It kind of has this turning point. It falls and then it turns. And it looks like mx squared plus b. So squared, it has sometimes changes its shape when it opens and closes. It might be opened much wider or much thinner. And it also has, y-intercept. It crosses the y-axis usually at a certain point. Okay, so that's what those look like, the difference between constant, linear, quadratic. Now let's focus on the different characteristics of our quadratic functions. So as I said to you, I'm going to try to focus more on the quadratics, just bring back the other two as a frame of reference. Quadratic functions have this parent function. This is the parent function. This is in standard form. Standard form, parent function. That means that it is kind of the basis for all other quadratics. Every other quadratic is some change, variation, transformation of this parent function. This is kind of the basic one, okay? Most quadratic functions have an axis of symmetry, so that is a line that splits it into two equal halves. Okay, splits the function into two equal halves. So if I'm going to list the axis of symmetry in this particular example, I'm going to say that it falls right here. That's the axis of symmetry, right? And the axis of symmetry is always a vertical line. At least the ones we're dealing with this year will always have a vertical line. And if that's a vertical line, then it has an equation of x equals some number. So where am I on the x? I'm intercepting the x at 0. So x equals 0 is the equation of your axis of symmetry for this particular problem, okay? The vertex is the point where the function intersects its line of symmetry. Point where the function intersects the AOS, axis of symmetry. Okay, the point of function, the point where the function intersects the axis of symmetry, the AOS. This is called the AOS. We sometimes abbreviate it, axis of symmetry, okay? So the point where my function's crossing my axis of symmetry is this point right here, and that vertex point, has a point of 0, 0, okay? 0, 0. In this example, there's your vertex. Sometimes I like to call it the turning point. It's the point where it starts to head in a different direction. It's kind of the middle point where it starts to, it changes direction. So it's reaching that point, and then from that point on, it starts off in a different direction. That's your turning point, your vertex. The maximum of your graph is the highest point on your graph. Highest point, the minimum is going to be your lowest point. And in this case, the highest point, we don't know because these arrows mean that it's going up forever and ever. We can't really dial in on exactly which point it is that's going to be the highest. So in this case, the maximum, we're going to say there is none in this particular example. And the lowest point in this example is its vertex. So oftentimes that vertex is the lowest point. And then when you flip it upside down and the parabola is heading in the other direction like this, then that vertex point is going to be your maximum point as well. Its highest point and its lowest point. In this case, the lowest point is 0, 0. That's your minimum, okay? Your intercepts are where it crosses the x or y axis. And usually when we're talking about intercepts in quadratic functions, we're usually talking about where it crosses the x-axis. When we're graphing it, we often want to know where does it cross the y because it gives us some perspective as to where to set it on the coordinate board. But typically when we're talking about intercepts, we want to know where does it cross the x-axis. And when we list intercepts, we usually just say it crosses at -5 or 2 or 7 or whatever. We don't give them as ordered pairs. So in this case, I would say where does it cross the x-axis? I would use these little fancy braces and say 0. That's the intercept. Crosses at 0. And we use these little fancy brackets because we're just listing numbers. If it crossed more than once, if I were dealing with a function that looked similar to this, I might have multiple places where it crossed the x-axis. And in that case, I would just list all those spots where it crosses and say that those were the intercepts, okay? End behavior. We started to talk a little bit about end behavior in the past. So really what we're just asking you is what's happening to these ends of the graph? What are they doing? And so think about this for a minute. You're either going to be going up over here in this direction forever and ever, or you're going to be going down forever and ever. And then on this side, you're either going to be going up forever and ever, or you're going to be going down forever and ever. So really we just have a combination. And so how do we write the end behavior? We use these kind of like an ordered pair, and we say on the left side of my graph, it is traveling upward forever and ever. So I do this. If it were heading down, I would kind of make the arrow go in the other direction, kind of point it down like I did here. And then on the right side of my graph, it is heading up forever and ever over here. So these two are what we call the cheerleader. They look like little arms that are kind of facing away from each other, right? So some teachers use this analogy like, oh, that's the cheerleader because they're heading in both directions, okay? If you want to come up with some silly little pictures for all the other ones to help you remember which one's which, that's totally fine. Even and odd, this refers to the power of the function. So since it's a quadratic and it has a power of x squared, it's an even function too. Okay? Positive and negative, that just means that in standard form in any function we have, right, we have, if it's linear, we have mx, right, linear is to the first power, plus b. If it's a quadratic, we have y equals ax squared plus bx plus c. We're referring to this lead coefficient, that number in the front. If it's positive, the graph is going up or in standard position. If it's negative, it has been reflected and it's headed down. This would be a negative function. It's the reflection of this positive function. Okay, so positive looks like the parent, and negative means it's been reflected down, so it's upside down. So in this case, in this example, we're dealing with a positive function. And then increasing and decreasing is something a little bit new to you. And it's just basically listing the sections of the graph that are increasing, that the y values are increasing, and in what section are they decreasing. So I'm going to ask you to kind of think outside the box a little bit here. Where is my graph increasing? So most students would say the whole thing is increasing because these arrows are going up, 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 okay? But what's really happening, if I were to draw my axis of symmetry, this line right here, as I'm approaching, because remember you read the graphs from left to right, so as I start over here and I read from left to right, I can see that I'm getting closer and closer and closer to zero. So this section of the graph is actually falling from left to right. Those numbers are getting smaller, 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 smaller. So I would say decreasing from negative infinity, so starting way over here, wherever we are, all the way to zero. It's going down, 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 down. So it's decreasing in that region. And then I would say that it is increasing, so starting at zero, again, I'm still reading from left to right, starting at zero, these values are going up, 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 up. So increasing is going to be from 0 to positive infinity. So where is it decreasing and where is it increasing? A strategy to help you with that sometimes is to take a full sheet of paper and start on the left side of your paper and just kind of slowly drag it toward the right side of the equation and watch what's happening to your function as it appears to you. Is it appearing that it's going upward, or is it going down and then down, 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 down until, it starts to turn and head in another direction? Stop and make your endpoint. It's going down from here to here, then continue with your piece of paper. Now it's going upward, drag your paper, continue to look at what's happening. It's going up, 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 up. Sometimes that helps to just kind of focus you in a little bit as opposed to looking at it as a whole like this. Okay, so now what we're going to do on the next page is we're just going to practice a couple, writing down some characteristics and figuring out, what kinds of graphs we're dealing with. So we're going to look at the second page, or third page, I don't know what page I'm on now. Characteristics, here we go. So looking at this first one, again, I just brought constant and linear back for some perspective. We don't always list all of this stuff. This is a constant function. I know right away that that has a degree of 0. This one's linear. I know right away that one has a degree of 1, and that's my parabola, has a degree of 2. Okay? So let's do the parabola one first. So the axis of symmetry is going to be right here, and that's going to be at -3. So that is at x equals -3, because remember that's a line, and we extend it to both sides of the graph, so that's the line x equals -3. The vertex is at this point, which is backward 3 and down 1, so the vertex is at -3, -1, backward 3, down 1. It does not have a maximum, but it does have a minimum. Its lowest point is its vertex, -3, -1. Intercepts, let's see, where does it cross the x-axis? It crosses at -4 and -2. So again, remember you just list those points. I'm really terrible at making those brackets, so it's okay if you are too. Those are really tough to make, those little braces. So these are the two places where it crosses the x-axis. Those are the intercepts, -4, -2. The end behavior, left side of my graph looks like it's going up, up, up. And right side of the graph is going up as well. So up and up, comma in between them, shows me the end behavior, okay? This function is an even function because it is a power of 2. That makes it even. And again, this parabola is heading upward, so it is in the positive. It has a positive a value in front of the equation. And let's talk about where it's increasing. So again, increasing and decreasing. So I'm looking for a place where from left to right, it's going up, up, up. And so this from left to right is going down all the way until I hit 0, or until I hit its vertex. And then it's heading up. So this is the increasing part, and this is the decreasing. This one's going down, okay? So increasing is from 0, ooh, not 0. Why not 0? Because I'm not at 0, I'm at -3 right there. We're always doing it in terms of the x-axis. So from -3 in this direction, my values are getting bigger, 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 bigger. So from -3 to infinity is where my graph is increasing. And then just to use a different color for you, -3. So from negative infinity all the way to -3, it's going down, 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 decreasing. So we would write it like this, from negative infinity to -3. So it's important, remember, that when you're listing this one, that you list from the left side of it to the right side, and then from the left side to the right side. We always read left to right. So you can see there's a lot to do in a quadratic function. Much of this does not apply to linear and constant functions, okay? We just want you to see the difference between all of these functions. We dealt with some constants, we dealt with some linears before. Now we're really stepping it up here with these quadratics. So let's go backward and go down one. Does the linear equation have an axis of symmetry? Could I draw a line and split it into two parts? I could, and I could do that multiple times. There's just too many of them to list. If I extend the line, I could draw another one over here and over here. So we just say, nope, that's not applicable because we just have too many of them to draw. Does it have a vertex? Nope, because it doesn't turn in any way. Does it have a highest or lowest point? Nope, because it keeps going in both directions forever and ever. Does it cross the x-axis? And this one seems to cross right here at -6. So I would say it has an intercept of -6. End behavior is pretty easy for lines. The left side's going up, the right side is going down. Notice the difference, up and down. Different than what we've been doing before, because both of those parabolas we did were heading up in both directions. So this is what happens when it looks like it's going down. It is an odd function because it is a power of 1. It is a negative function because it's going downward from left to right. And again, all of it is either increasing or decreasing, so there's no turning point to tell where it suddenly starts to turn directions. So these are not necessarily doable. So you can see there's very little of what we do with parabolas that sort of pertain to these things, okay? Constant degree of 0 does not, again, has way too many axes of symmetry to write down. Doesn't have a turning point or a vertex. Does not have a higher or lower point. Does not cross the x-axis anywhere. Its end behavior is flatline, so we don't talk about it. It's not going up or down. It is neither an even or odd function because it's a power of 0. It's not positive or negative, and it's not increasing or decreasing. So you can see that these constant functions are pretty bland, and then we step it up a little bit with our linear functions, but then our quadratic functions really get quite complicated, and we have a lot to talk about. On the last page, I'm going to leave this one for you to do, this parabola one. I want you to try this one. Use the one on the last page as an example. And then I do want to talk to you a little bit about piecewise functions. So these guys are functions. It's a function with different rules for different parts of its domain. Remember, domain is X. Oops, different parts for of its domain. Remember, that's your X. So you can see that there's two kind of parts to each of these functions. They have different rules. Different things are happening for those sections, right? When you see a piecewise function written, usually it says y equals, and there's this giant brace like this, and then there's one equation here with its rule, what part of it, and then there's the second equation with its rule, and then if there's a third, there's a third. There could be multiple pieces. There's no rule on how many of these there are. So before we start this function, I want us to just look at what it looks like, what is happening to it. So let me scroll my page up a little bit. I'm going to get rid of that because I want to write underneath. I'll put the equations underneath. Okay, so in the first example, what's happening is y equals, I have two equations. I have two sections of my graph. You can see it's kind of split right here and right here. Seems to be the two endpoints, okay? So from left to right, so from out here all the way to -1, I have a constant line, okay? And that constant line is crossing my y-axis at 2. So that is going to say y equals 2. That's the equation of that line, y equals 2. All right? But I only want the part of the line y equals 2 from -infinity up to -1. I don't want the rest of it. It's been cut off. So the rule is that I want the x values between -infinity and -1. That's the section I want, and that's it. Notice how I wrote that as a compound inequality. I want my x values between this endpoint, -infinity, and this endpoint, -1. And these are always, the infinity is less than or equal to these values, and these values are less than or equal to -1. That's just the order you always put it in. We'll practice this more. The second part of my graph starts at 0, and heads, again, left to right, starts at 0 and goes in this direction toward positive infinity. And in this section, I actually have a linear equation. It looks like it crosses the y-axis at 1, and it has a slope of down 1, 2, and over 3. So it has a -2 over 3, so -2/3 slope. So that looks like the equation -2/3 crosses the y-axis at +1, and I only want a section of that line from 0 to positive infinity. So from 0 to infinity. So I only want the x values in between 0 and infinity. So I have my equation and my rule. I have my equation and my rule. Okay? So this function doesn't have a degree because it's a broken function. It does not have an axis of symmetry because it's broken. It doesn't have a vertex because it's been broken. It doesn't have a max or a min because it's broken. Part of it has an intercept, but not the whole thing. So we're going to say, nope, it's been broken. End behavior, again, since it's a broken piecewise function, we don't necessarily talk about that. It could, one side is constant, so odd, no degree, and one side is linear, so degree of 1. So again, because it's two different things, we don't really do a whole lot with it. It's not positive or negative. There's no increasing or decreasing sections. You could say it increases or decreases. There is no increasing section, but you could say that it's decreasing from 0 to infinity. If you wanted to say that that piece was decreasing, that would be acceptable. So piecewise functions very similar to linear and constant in that a lot of what we deal with quadratics doesn't necessarily apply to them because they're broken graphs. They don't hold the same properties as a quadratic does. So we're really just wanting you to see the difference between what we've been doing before with lines and constant graphs and what we're doing now with quadratics. They're very different, they act differently, and they have different sets of rules. Okay, so it's typical for students to say, oh, I'm just going to treat this like a line and I'm going to do what I do when I do lines, and you can't always do that. I'm going to write the equation for this one for you, and then I'm going to ask you to fill in this information. So again, I have a line right? This is a negative slope. Let's see, it's probably down 1, 2, and backward 1, 2, 3. So down, no, I'm sorry. I'm totally wrong on that. It's not a negative slope. That's a positive slope. That line, I should have drawn this first, from left to right is rising. That line is rising. So it's actually going, I'm going to say up 2 and over 3, positive 2/3 slope. So we're going to have y equals 2/3 x. I don't know the intercept. I'm going to say if I continued the line, it would cross somewhere between 3 and 4. So I'll say plus 3.7. I'm just estimating. And I only want the values from negative infinity to -1. So that's the rule part. Okay, so that's your first line. And then the second piece, this looks like half of a parabola, starting again at the cutoff of 0 from left to right. So parabolas have the equation x squared, and it looks like it crossed the x-axis, or the y-axis, sorry, at -2. So -2. And I'm going to say I only want that piece from 0 to infinity. So there's your equations for you. I want you then to answer these questions and then go ahead and do this one as well, and we'll talk about them when you come to class.